There is a principle that goes hand in hand with Varignon's theorem. It's called principle of transmissibility. These two powerful duo make finding moment about a point, in my opinion, a little bit more fun. So why don't we investigate what this principle is all about? Principle of transmissibility states that shifting the point of application of a force acting on a body to another point on the line of action of the force without changing its direction causes no change in the equilibrium state of the body. Well, that's certainly quite a mouthful. Why don't we try to decode that statement? According to this principle, if we are interested in shifting or moving the point of application of a force to another point, as long as we stay on the line of action of the original force without changing its sense of direction, of course, we may certainly do so because it causes no change in the equilibrium state of that body. Well, an easy way to remember this principle, a car would not know the difference whether you push the car at its rear end or you pull it from its front end, as long as these three things are true. Number one, if you prefer to pull instead of push, make sure that the line of action of the pull is the same as the line of action of the original force, which is the push. Number two, you don't want to change the magnitude, of course. And thirdly, you do not want to change its sense of direction. The push acts to the right. Therefore, if you prefer to pull instead of push, make sure that pull is also acting to the right. According to this principle, it causes no change in the equilibrium state of the car. The car would not know the difference whether you push or pull, as long as those three things are true. Why don't we apply this principle to our problem? This is the exact same problem as in the previous two lectures. We are still interested in finding the moment of the 500-pound force about point A. We're still interested in finding the measure of the tendency to rotate the 500-pound force about point A. So first and foremost, I'd like to establish the line of action of the 500-pound force. It is this pink line of action. This is a 36-foot pole. It extends in the horizontal direction 12 feet. The point of application of the 500-pound force is at the left end of this horizontal extension. According to this principle, I am allowed to shift or move the point of application of the 500-pound force anywhere that I'd like, as long as I stay on the line of action of that force. Well, I'd like to move it to this point where it intersects with the 36-foot pole. We make sure that the magnitude stays the same, 500 pounds of course. We make sure that the sense of direction stays the same, and we are on the line of action of the original force. Well, according to this principle, this will cause no change in the equilibrium state of the pole. The pole would not know the difference whether you apply the 500-pound force at this point or at this new point of application. Well, in conjunction with this principle, I'd like to use Varignon's theorem. If you recall Varignon's theorem, it states that the algebraic sum of the moments of the components is equal to the moment of the resultant. So instead of focusing on the resultant itself, I'd like to focus on its two components. The two components, according to an earlier lecture, it's 300 pounds in the x direction and 400 pounds in the y direction. So let's get rid of the resultant. We'd like to focus on these two green components. Let's, before we start our calculation, make sure that we know the lengths and the distances necessary to find moment about point A of these two components. I'll start with an angle which I think we have calculated in an earlier lecture. This is arctangent of 4/3, and that's equal to 53.13 degrees. So therefore, according to the definition of tangent, tangent of 53.13 is equal to opposite over adjacent. I'll call this opposite side, opposite of the angle, as distance A. According to the definition of tangent, it's opposite over adjacent, A over 12. So therefore, if you solve for A is equal to 16 feet. The height of the pole itself is 36 feet, so therefore if A is 16, then from that point to point A, that is 20 feet. Well, let's apply Varignon's theorem. Moment about point A is a vector, and according to Varignon's theorem, that is equal to moment about point A of the 300-pound component plus moment about point A of the 400-pound component. Let's take a look at these components one by one. An easy way to find moment is force times distance. However, those two, they have to be perpendicular to each other. Let's start with the 300-pound component. 300 is the force, the perpendicular distance to reach to point A. The line of action of the 300-pound component is in the horizontal direction, so therefore the only perpendicular distance to reach to point A is 20 feet. That's the only perpendicular distance. How about the next component? 400 pounds is the force, and the only perpendicular distance to reach to point A, well, the line of action of 400 is in the y direction. So therefore, there is no perpendicular distance to reach to point A because that component goes through point A. 400 times 0. 0 is the perpendicular distance. There's no perpendicular distance. I've established scalarly moment about point A of each component. Let's establish sense of direction. Positive x is to the right according to this coordinate system. Positive y is up. Therefore, positive z points out of the screen, and if you point your right thumb out of the screen, your forefingers will want to curl in this particular direction. Therefore, this particular direction, counterclockwise, is what is considered as positive moment. And you take a look at the first component. You want to draw an imaginary circle which centers at point A, and you ask yourself the question, how does the 300-pound component want to rotate around that circle about point A? It wants to rotate clockwise. And since counterclockwise is considered positive, therefore I must put a negative sign in front of that first term. Well, the second term is 0 anyway, so it doesn't matter plus 0 or minus 0. You calculate this, this comes out to be equal to negative 6,000, and the unit is of course feet pounds. Moment about point A is a vector, and the magnitude is equal to 6,000 feet pounds. The sense of direction, because we have a negative sign, negative of counterclockwise is of course clockwise. This is exactly the result that we had calculated in the previous two lectures.